Let us consider a boy of mass 50 kilogram. A boy of mass 50 kilogram stands inside a lift. Let us consider a boy of mass 50 kilograms stands inside a lift. Okay, so there is a lift and there is a boy standing inside the lift. Okay, so the question number one. Question number one, draw the free body diagram. Draw the free body diagram of the boy. So draw the free body diagram of the boy. Okay, so you had to mark the forces acting on the boy, and then you can, if you want, you can send it to me through chat box so I can view your answers. I mean your drawing. Okay, so this is not that hard. Okay, we have only two forces acting on this boy, right? So one is weight of this boy, which is gravitational acceleration, sorry, gravitational attraction force, which is mg, right? So now here the mass is given as 50, no? So therefore you can find the weight, W equals m into g. Therefore m is 50 into 10, 50 kilogram into 10 meter per second squared, so it will be 500 Newton. So you can mark here mg or you can mark 500 Newton here, both are fine. So then normal reaction force vertically upward from his foot, R. So these are the only two external forces acting on this boy. Okay. So here mg is weight, 500 Newton.
So should
So
the normal
mg
reaction
equals,
be equal to the weight of the boy?
sorry?
The normal reaction, should it be equal to the weight of the boy?
Yeah, when the object, the boy is, the object is the boy. So he is at rest now. The lift is just staying there, okay? So in this case, R equals mg. Normal reaction force equals to the weight, okay? So then R equals 500 Newton. Okay? Is that clear?
Yes, sir.
Okay. And then question number 2, find the normal reaction force. Find the normal reaction force acting on the boy. Acting on the boy find the normal reaction force acting on the boy in find the normal reaction force acting on the boy in following cases. in the following cases. So the first one, so I can take Roman number 1. Yeah, if the lift is at rest, if the lift is at rest, the lift is at rest. So that's when the boy and the lift is at rest, then we know that R is equals to mg, right? According to Newton's first law, if the object is at rest or moving at constant velocity, there is no any unbalanced force, right? Therefore, R must equals to mg. Therefore, R equals 500 Newton. Okay. Therefore, R equals 500 Newton. And Roman number 2. Roman number 2. So this one also you have to tell me. If the lift moves vertically upward with constant velocity. Okay, so what happens? What is the value of the normal reaction force when the lift moves vertically upward with a constant velocity? What happens to the normal reaction force? I mean, what is the value of the normal reaction force if the lift is moving vertically upward with a constant velocity?
The same value as the weight.
Yes. So again, now we know according to Newton's first law, the Newton first law says unless an external force is applied, the object at rest remain at rest. The object in motion remains at constant velocity. So we can decode this as if object is at rest, then there is no any external force acting on. There is no any unbalanced force acting on the object. Therefore, the forces must be balanced. Likewise, if an object is moving at constant velocity, then there is no any unbalanced force. Therefore, all the forces are balanced. So therefore, again, we can write R equals mg. So here again, R is equals to mg. So R equals 500 Newton, right? So if the lift is at rest, the normal reaction force is equal to the weight of the boy. Or if the lift is moving at constant velocity, there also the normal reaction force will be equal to the weight of the boy. Is that clear?
Yes, sir.
Okay. And the third question, Roman number 3. The lift is moving vertically upward. The lift is moving vertically upward with a constant acceleration of 2 meters per second squared. So Roman number 3, the lift is moving vertically upward with a constant acceleration of 2 meter per second squared. So what would be the value of R? Try to find it. If you get the value, if you got the value, you can send it to me through chat box. Sorry?
Can you repeat the question maybe? Sir?
I didn't hear you clearly. I mean, your voice is a little bit breaking.
So can you repeat that question again?
Yeah, sure. Now the question is this. Here the question number 2, did you write find the normal
Yes.
reaction force in the following cases? So
Yeah.
Roman
I
number
need
1
the third one.
when the lift is at rest. Roman number 2 when the lift is moving at constant velocity. And here the Roman number 3, lift is moving vertically upward with constant acceleration of 2 meter per second squared. The lift is moving vertically upward with a constant acceleration of 2 meters per second squared. Okay, so here what we can do is I can consider by applying F equals ma to boy. So I can apply vertically upward F equals ma. So if you consider the vertical forces acting on the boys, only the normal reaction force and the mg. So normal reaction force is vertically upward r. Here we are considering vertically upward direction, but weight is downward, so it's minus mg equals mass times acceleration. So therefore r equals m g plus ma. So therefore r equals m g plus a. So therefore r is equals to mg plus a. So then now we know the value of g and a. Therefore r equals m is 50. M is 50 plus g is 10 plus 2. Therefore r equals 50 into 12. So r is equals to 600 Newton. So now you can see r is greater than mg. So in this case r is greater than mg, right? Then the normal reaction force is greater than mg. That's why you will feel a force. You feel like you get heavier when the lift start to accelerate. So now you are in, for example, let's say you are entering a lift, and when you push the button, so it's accelerate, right? During that acceleration, you feel like you will be extra pushed to the ground, or you feel like much force on your feet. Is that clear? Hirosh, පැහැදිලිද?
Can you explain that again?
Yeah, sure. දැන් මෙතන r equals mg plus a form expression එක එන එක පැහැදිලිද? By applying F equals ma.
No, sir.
No. Okay, so here we are applying F equals ma to the boy. එතකොට මේ ළමයා ගත්තා නම් මෙයා ළමයා මත ක්‍රියා කරන forces තියෙන විදියට තියෙන්නේ මේ r එකයි mg එකයි. හරිද? That is the normal reaction force acting on the feet by the ground of the elevator and the weight acting on this boy, right? So then I can write I'm using F equals ma vertically upward. උඩට පැත්තට ක්‍රියා කරන බල තියෙන්නේ r. So r minus mg is equals to mass times acceleration. F equals ma. මෙතන අපි දාන්නේ net force. හරිද? ඒ කියන්නේ සංප්‍රයුක්ත බලය. The resultant force. So in vertical direction, in vertically upward direction, we have a resultant force of R minus mg. Okay, do you understand the writing of R minus mg?
Yes.
Okay, so that is the resultant force acting on the buoy. So that is equals to mass times acceleration. So if you subject for R, then R equals mg plus ma. So you can then take m as the common factor. So then R equals mg plus a. So methana, it's like a net acceleration. This gravitational acceleration, and no, I'm not going to explain that here. It just so you can take R equals mg plus a. So do you understand the derivation of this formula?
So what I can't understand is how the R minus mg is equal to ma.
Yeah, so this is the resultant force. So F equals ma. Right now, for example, you studied this. No, you apply one force here. Let's say 20 Newton, 30 Newton, right? And then this side, let's say 10 Newton, and mass is 1 kilogram, right? Then to find the acceleration, we did similar this kind of question, right? So therefore, first you take the resultant force, 20 and 30, 50, 50 minus 10. So here you have 20 plus 30 in this direction minus 10, because 10 is in the opposite direction. Mass is 1 kilogram. So I can 1 into acceleration is a. Therefore, a equals 20 plus 30, 50, 50 minus 10 is 40, 40 divided by 1. So a equals 40 ms minus 2. Right? Likewise, similarly, we apply for the buoy. So if you consider the buoy, the forces acting on the buoy is R and then mg. So I'm applying vertically upward. So in upward we have R, but mg is in downward. So this will be the resultant force. So this resultant force equals to mass times acceleration. Is that clear now?
Yes.
Okay. You sure, right? If you still didn't get it, let me know. It's totally fine explaining once again. I sure? Is it clear? Hirosh, is it clear?
Is it the
Yeah.
2ms 2ms minus 2 equal to with that Boy's mass to the R minus mg?
Yeah, so here actually R minus mg equals mass times acceleration. Now acceleration is actually 2. I have taken as a variable a. I take it as a. So otherwise you have to put here 2. Mass times 2 meters per second squared. Right? Is that what you asked?
Okay, sir. Oh, I got it.
තේරුණා නේද?
Yes, I was confused with like G is always gravitational force, so it is downward, and here acceleration is upward. So I thought we have to subtract the acceleration from that gravitational acceleration.
No, here we have to consider the direction. Now I am applying vertically upward. No, in upward force we have only R, and then mg is a downward. So therefore it's minus R minus mg. So this will be the resultant force in vertically upward direction. So R minus mg equals mass times acceleration. So you clear, right?
Yes.
Okay. So then you can use this formula whenever the lift is accelerating vertically upward. So when an lift is accelerating vertically upward, So this is the formula for R. R equals m times g plus a. So you can straight away use this formula. Now, for example, in MCQ, they will ask, what is the value of R? Then straight away you can write m. So g is 10, we know, and let's say it's accelerating with 5 meters per second square. Then you can take here 10 plus 5, 15 into the mass. Like that, you can calculate for R, right? So you can remember this formula whenever the lift is moving vertically upward. Okay. Right. So here, therefore, mass is 50 and g is 10. Acceleration is 2 meter per second squared. Therefore, the normal reaction force we obtained 600 Newton. So in this case, you can see R is greater than mg because mg is 500 Newton, right? The mass times mg equals mass is 50 and g is 10 meters per second squared. So if you multiply 500 units of Newton, right? We calculated this earlier. So therefore, you can see here in this case, R is greater than mg. So you can note down that. So the normal reaction force, you can write in words as well. The normal reaction force is greater than the weight of the boy. That's why you feel you are a bit pushed towards the ground, towards the floor when the lift start to accelerate. Have you experienced that when you are moving in a lift?
Yes, sir.
Okay. So now the Roman number 4, this one you calculate. Lift is moving vertically upward with a constant acceleration of 4 meters per second squared. 4 meters per second squared.
Is it 700, sir?
Sorry?
700 Newton?
700. Okay, so here we can use this formula because if you apply F equals ma for this case, you will again get this formula only. So then straight away I can use R equals m g plus a. Therefore, R equals 50 into 10 plus 4, 14 into 50 is 700 Newton. Okay, good. Okay, for practice, I'll give you one more. Question number 5. The same question, but take the acceleration is 6 meters per second squared.
Newton.
800 Newton, no? Okay,
Sir,
correct.
I
And
have
yeah,
a question. So gravitational acceleration is in downward direction, right?
yeah,
Here the acceleration on the system is on the upward, but when we
yeah. The
are
system is accelerating with 2 meters per second squared. Okay.
so
So here, this actually you can think of as yeah, R equals m g plus a, right? So yeah, it's like some net acceleration. It's like a net, something like net
sir, but
acceleration.
if we get the resultant acceleration of that two accelerations, gravitational acceleration and system acceleration, it will be
Mm.
opposite direction. So They will be subtract from each other.
No, here, now if I drop this, it will fall with acceleration, gravitation acceleration, right? But what I'm doing is, I hold this and accelerate with, for example, 1 meter per second squared. I hold this and I accelerate. Each second, the velocity will increase by 2 meters per second. Do you understand?
Yes.
So here in this case, now this is the cable. You can see the cable. The cable is connected to the motor, right? So the motor is it rotates and it will push this lift to upward with this acceleration. So this entire lift is moving with this acceleration, 2 meter per second squared. Okay,
Yes.
is that clear?
Yeah.
Okay, and Roman number 6, V1. Okay, so the Roman number 6, lift is moving vertically upward. The lift is moving vertically upward with a uniform deceleration, of 2 meters per second squared. With a uniform deceleration of 2 meters per second squared. Okay, so you know deceleration means negative acceleration. So then I can apply F equals ma vertically upward. So R will be the upward minus the weight downward and mass times acceleration. So here it is a deceleration. So therefore minus A. Negative acceleration is the deceleration, right? So then therefore I can write R equals, the minus mg come to the other side as plus mg minus ma. So therefore R equals mg minus a. So you can use this as a formula when the lift is decelerating vertically upward. So this is when the lift is accelerating vertically upward, and this is when the lift is decelerating vertically upward. මේ දේවල් අනිවාර්යෙන් අමතක වෙන්න බෑ. ගණන් හදලා පුරුදුම වෙන්න ඕනේ. lift එක vertically upward accelerate වෙනවා නම් R equals mg plus a. lift එක vertically upward decelerate වෙනවා නම් R equals mg minus a. because MCQ වල දැන් ඔයාට මෙන්න මේ ටික ඔක්කොම ලියාගෙන ඉන්න බෑ. මේ ඔක්කොම ලියන්න නැතුව ඔයා ටයිම් එක සේව් කරන්න ඕනේ. එතකොට මේවා ගණන් හදලා ප්‍රැක්ටිස් වෙන්න ඕනේ. හරිද? Okay. So when the lift decelerates vertically upward, the formula is equals to R equals mg minus a. Is that clear?
Yes.
Okay, then now we can find the value of R. So therefore, R equals to, mass is 50, G is 10 minus 2. Deceleration is 2. So therefore, R equals 50 into 8. R equals 400 Newton. Right? So here, you can see R is smaller than mg. So that's why දැන් ඔයා lift එක නගිනවා. හරිද? lift එක නගිනකොට ඔයාගේ destination flow එක click කරනවා. click කරපු ගමන් මොකද වෙන්නේ? දොර වැහැලා it start to move. When it start to move, it's starting from rest. Starting from rest means zero velocity, and then it's moving with, it's gained some velocity. That means velocity has changed, it has accelerated. During this acceleration, you feel your legs are being little bit pushed toward the floor. You feel like you get more weight. That's why R is greater than mg. But now let's say the lift is after accelerated, it's moving with constant velocity. When the lift moves with a constant velocity, then what happens? You feel the same weight, right? That means R is equals to mg. The normal reaction force is equals to the weight. And then now let's say you reached your destination floor, and what happens? The lift will decelerate. When the lift is decelerate, lift you feel you get little bit සැහැල්ලුවක් දෙන්න. Lift එක නවත්තන්න කලින් you feel some a relief, like you've been a little bit සැහැල්ලු ගතියක් තේරෙනවා. Have you felt that when you are moving in a lift?
Yes.
So අපි අර ඒක වේගයෙන් ඇවිල්ලා decelerate වෙනකොට you feel you bit little bit weightless. Okay, weight එක පොඩක් අඩුවෙන් තමයි felt වෙන්නේ. That is because during the deceleration the R value is less than mg, so it will be 400 Newton, right? Okay, and Roman number 7 V2, the same question, but deceleration is 4 meters per second squared, right? Can you find the value of R? So the lift is moving vertically upward with a constant deceleration of 4 meters per second squared. 300 Newton, correct. So here you can take this formula, R equals 50 times 10 minus 4. So therefore R will be equals to 300 Newton. So because 50 into 6 is 300 Newton. Okay. And Roman number 7, 8, V3. Same question, you take this as 6 meter per second squared. Two hundred, okay. And then Roman number 9, 1x. Let us consider the lift is moving vertically downward with constant acceleration. So write down the question, Roman number 9. The lift is moving vertically downward with a constant acceleration of 1 meter per second squared. 1 meter per second squared. 1 meter per second squared. Okay, so now the lift is moving vertically downward. I think it's Shamin, right? Okay. So actually, in online classes, I didn't start the mechanics yet because that your batch I dropped that. So this is actually our physical class. We had a physical class. There we are going. We started mechanics, and then now we shifted from physical to online due to certain reasons. So that's why. But anyway, now I have started 2 online classes on Sundays. That's hybrid classes. Sunday morning, 8:30 to 11, and Sunday again 1:30 to 5. So these classes I'm doing as hybrid. So once I started mechanics there. By the way, for you, I think in the first unit I have done only up to dimensions part. So if I'm starting vectors, I will let you know for sure. Okay. Okay, so now in this question, the lift is moving vertically downward with the acceleration of 1 meter per second squared. Therefore, since acceleration is vertically downward, I'm applying F equals ma vertically downward. So applying F equals ma vertically downward to the boy. So here downward F equals ma. So now if I consider downward motion, the force acting in downward is the weight mg, and minus r is upward. So it's opposite to the direction that I'm considered. So mass times acceleration also downward. So therefore, in this case, r equals, if you take r to the other side and ma to this side, r equals mg minus ma. Therefore, r equals mg minus a. So remember, when the lift is accelerating vertically downward also, then r will be mg minus a. R is equals to mg minus a. Did you understand this?
Yes, sir.
Okay. So then we can put the values. So r equals 50 into 10 minus 1. So r equals 10 minus 1, 450 Newton. 9 into 50 is 450 Newton. Okay, so Roman number 10. Roman number 10. The same question, but this time accelerating with vertically downward. Let's say 4 meters per second squared.
Three hundred. Is it 300 Newton?
It will be 300 Newton. Yeah. Okay, the next question. The same question. This time you take acceleration is 6 meters per second square. R equals 200 Newton. The next question, take the acceleration as 8 meters per second squared. The same question, the lift moves vertically downward with constant acceleration of 8 meter per second squared.
100 Newton.
100 Newton, no? 10 minus 2 is 2. 10 minus 8 is 2. 2 into 50 is 100. Okay. The next question, the same question, but take 10 meters per second squared.
Zero.
Sorry, I didn't hear you.
0.
0, yes. So why it is 0? What does it mean? What is the physical significance of it?
There's no force.
Sorry?
There's no reaction force acting on the.
Yeah, because you can see 10 meters per second squared is the gravitation acceleration. It's like free fall. Right? උදාහරණයට ඔයා ලිෆ්ට් එකේ ඉන්නකොට no. So ලිෆ්ට් එකක කවුරු කෙනෙක් ළමයෙක් ඉන්නකොට කේබල් එක කැඩලා ලිෆ්ට් එක වැටෙනවා. එතකොට ලිෆ්ට් එකයි ඒ කැටලා ඉන්න ළමයයි දෙන්නම free fall එකේ වැටෙනවා. Understood?
Yes, sir.
Is that clear? Now, for example, let's say You can see myself in the video, right?
Yes, sir.
Okay, so I'll take this. Okay, so here this is the lift and this is the boy. So what happens is both will fall under the gravitation acceleration. Okay, so here the both will fall. Now if I drop these two at the same time, right? Then what happens? Both will fall in the same rate, so that there won't be any normal reaction force acting on the ball. Do you understand? It's like it's, it's like he'll feel that he is floating inside the lift.
Yes, sir.
Now there is some leisure place in I think Japan or Malaysia or something. Some Japan, Singapore, or Malaysia, some one of those country have a leisure park, something like now here uh, in Sri Lanka we have leisure world. Likewise, they have some leisure park. They have this thing. They can uh, experience the free fall. Like for example, they have this lift and then they drop. I mean, they won't drop. It's actually little by little, it will accelerate and accelerate and accelerate and acceleration increase to 10 meters per second square. So when it reached to 10 meters per second square, when it reached the value of gravitation and acceleration, the people inside will, the person inside that will be feel he is like floating. Now, for example, let's say that lift is entirely covered and can't see the outside, then he doesn't feel like he's accelerating. He feel like the lift is at the same place. He is floating inside, like he is in the space. Do you understand? But if there is a hole or window in the lift, then he will realize since the things are moving relatively go up, then he think, then only he realize, oh my God, I'm falling with the lift. Do you understand? Otherwise, he feel he is floating inside the lift. Do you got me?
Yes, sir.
Okay, so as I told you, there is a leisure place. They have created like that elevator. So that elevator accelerated and reached to the gravitation acceleration. So that person will feel that he is floating, and then that inside the entire wall is made with digital screen, so that the screen will appear like space, outer space. The galaxies, stars will be there, so it's like you are inside the space. Then you feel you actually feeling the floating, and then you are in space. That's a very would be a nice experience. You can. I'm not sure which country it is. Might be Japan or some other country. Most probably like Japan, I think. Do you understand?
Like it is a space simulator. Like,
Yeah.
yes, sir.
Okay.
Thanks.
And the next question. This question would be funny. The same question, but take acceleration as 12 meters per second square.
Reaction force will be to the downwards 100 Newton.
Yeah. So what does it mean? What does it mean? Why it is 100 meter, 100 newtons minus downwards? Can you explain? Why it is getting negative value?
Because
physical theory
acceleration.
මොකක්ද?
acceleration of the elevator is higher than the gravitational acceleration.
Yeah, gravitational acceleration. So what happens to the boy inside the lift?
He will hit the other side of the elevator, like upper side of the.
Yeah, ගීල ඔළුව වදිනවා මේ උඩ down ගාලා. එතකොට normal reaction force එක තියෙන්නේ මොන පැත්තද? මේ පැත්තේ downward. Understood?
Yes.
Okay. So that's the reason. Okay, so do you understand with this elevator thing?
Yes, sir.
Okay, so if you have any questions, you can ask. By the way, are you practicing any questions related to these lessons like units, dimensions, and
Yes, sir. I
motion?
did those books on kinematics. I have some questions to ask. I'll ask them on next class.
Yeah, maybe you can send it to me through WhatsApp prior to the class, so that we can discuss that at the beginning of the class. Okay.
Okay.
Okay. Right. So we studied gravitational force and then a normal reaction force. So right on the next topic, tension force.
In the last one with that normal reaction force and the elevator, what is the when the lift is moving vertically downward with constant deceleration, is it equal to the lift is moving upward with constant acceleration?
Can you repeat again?
In here, sir, if we consider the lift is moving downward with constant deceleration, is
Moving downward with constant deceleration, yes.
Is it equal to the is the value equal to the case if elevator is constant in acceleration to the upward side?
So you're asking moving downward with constant deceleration. Downward with deceleration is similar to upward with acceleration. Is that the question?
Yes, sir.
Okay, so when acceleration in upward, so then we have R equals mg plus a. But when the lift is moving downward with deceleration, so we can use F equals ma downward mg minus R equals mass times acceleration. So R equals again m. So it goes to this side. This one comes to mg plus a. Yeah. So it will have the same value. Now, if the deceleration has the same value as acceleration, then R will have the same value. Okay.
Okay.
Okay. Okay. So write down the topic tension. Tension we usually mark with letter capital T. Weight W. Normal reaction force capital R. Tension we mark capital T. Yes,
yeah. Is it the next mechanical force?
Yeah. So we are discussing types of forces now.
Yeah.
Right? Types of mechanical forces. So one is weight, gravitation attraction force, and then we discuss normal reaction force. Now the tension. After the tension, we will be discussing friction.
Okay.
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 Right. එතකොට මේ ටෙන්ෂන් ආතති බලය කියන කතා කරන්නේ ඇදී තන්තු වල හා දඩු වල ඇති දඩු වල ඇතිවන බල. right? So the force again given the force generated in at the tantu. Yeah. So here we can write tension force. Yeah, the force generated in stretched strings and rods. Okay. Right, so here let us take, so after that write down, let us consider mm, yeah, let us consider an object of mass M, capital M, is held by a string mass hanged by a mass. Sorry, let us consider an object of mass capital M is hanged by a string attached to a rigid support. Okay. So then I'll draw the system. Here's a string, and then there is a mass attached to it. Okay, so we can mark the forces. Say so. This mass is attracted by the gravitational attraction, so its weight vertically downward, mg. So this weight pushes this mass vertically downward, right? But it is not moving downward because of the counter force acting on the mass by the string. So let's us mark that is the tension acting on the box by the string. Let's us take that is T1, and equal and opposite force, tension force, will be acting on the string by the so equal and opposite tension force acting on the string by the mass. because the mass pulls the string vertically downward because of the weight. The weight pushes the mass downward since the string is connected to the mass. So the mass pushes the string vertically downward. If the gravity is not there, then the mass will not push the string vertically downward. Do you understand?
Yes, sir.
Okay. So G is the weight of the object, and T1 is so this T1 is acting on the object. So tension force acting on the box, on the object, acting on the object by the string. තන්තුවෙන් වස්තුව මත ඇති කරන ආතති බලය. And T1 is the tension force, this one. This one is the tension force acting on the string, by the object. So here if you connect tension force acting on the string by the object, if you consider this as the action, then the other one is the reaction. Newton's third law: every action has equal and opposite reaction. This is the action and this is reaction. And we studied that under the Newton's third law, this action reaction is always acting on two bodies, not on the same object. Do you remember?
Yes, sir.
Okay. Then similarly, I can mark here this T2, and here again T2. So this T2 is the tension force acting on the support by the string. And this is tension force acting on the string, by the support. So here if you consider this as the action, then this is the reaction. Okay, quickly note down this. සෑම ක්‍රියාවට විශාලත්වයෙන් සමාන වූද දිශාවෙන් ප්‍රතිවෘද්ධ වූද ප්‍රතික්‍රියා බලයක් ඇත. Every action has equal in magnitude, opposite in direction, reaction force.
Okay, sir.
Okay. Now I'm going to consider the free body diagram of the mass and the string separately, right? So free body diagram of the object. So if you consider the object, then let's say this is the object. So then what are the forces acting on the object? So if we consider the free body of the object, then we have to mark only the forces acting on it. So it's weight vertically downward, capital Mg, and then there is a tension force acting on the object by the string. So that is vertically upward, T1. So now since the object is balanced, it's in equilibrium, so it is not moving, it's not accelerating. Here T1 must equals to capital Mg, right? By the way, let's say here the string is, I didn't mention in the note, let us consider object of mass m is hanged from a string. I didn't say as light string. So then let's say it has a weight, the string has weight, let's say its weight acts from its center of gravity, simple mg. So this is weight of the string. Okay, so this is the free body diagram of the object, and then I can write the free body diagram of the string. Free body diagram of the string. So then I have to consider separately only the string. Okay. So what are the forces acting on the string? So let's mark the forces acting on the string. So we know its weight will be vertically downward, mg, and then here T1, from this end there is a T1 force acting on the string. So T1, and this side there is another force T2. So you can see then if you consider only the forces acting on the string, so one is downward T1 and then from the up end T2. The make a force T1 T2 දෙක බලන්න තන්ත්‍රයෙන් එළියට act වෙන. ඒ කියන්නේ you are trying to stretch it. Do you understand? So therefore the string is under tension. ආතතියකට ලක් වෙලා තියෙන්නේ. Is that clear?
Yes.
So string එකේ කෙලවර දෙකෙන් force apply කරලා තියෙන දෙපැත්තට. එතකොට මොකද ඒක ඇවිල්ලා tension force එකක්, ආතති බලයක්, tensile force. So the tensile force එකේ opposite word එක තමයි compressive force. ඒ කියන්නේ දැන් දඬුවක් තියෙනවා ඒකේ මැදට ඔබනවා දෙපැත්තෙන්ම. එතකොට ඒක compressive force. Now this is a tensile force, tension. Is that clear?
Yes.
Okay, by the way, do you get a complete idea about the free body diagram?
Yeah.
Now, do you got a complete idea about a free body diagram? Free body diagram එක කියන්නේ ඒ object එකට මත ක්‍රියා කරන external force ටික විතරක් ලකුණු කරනවා. දැන් බලන්න මෙතන උඩ කෙළවර ගත්තා නම් we have this T2 downward also, but it is actually acting on the support. එතකොට ඒක අපි ලකුණු කරන්න යන්නේ නැහැ. ඒක act කරන්නේ support එක. Understood? So a free body diagram means you have to mark all the forces acting on that particular object. Is that clear?
Yes.
Okay. So now let's write down some important facts regarding the tension force. Write down. So you can give a small heading as important facts regarding the tension force.
One question.
Sorry.
Is sir, I have a question. Is the gravitational acceleration force weight is starting from the center of gravity or the bottom point of the object? Always.
Center of gravity. Sampurni මොකක්ද ඇවෙත් කියලා මට clear නැහැ. Can you repeat? You can repeat in Sinhala or in English, doesn't matter.
Sir, මේකේ weight එක weight
Oh.
force එක act කරන්නේ body එක center of gravity ඉඳන්ද නැත්නම් ඒකේ body එකේ bottom ඉඳන් act ඒක ඇද්දත් කමක් නැද්ද?
Center of gravity එකේ. යම් object එකක් ගත්තා නම් ඒකේ center of gravity එකෙන් තමයි weight act කරන්නේ. Now for example, if you take a solid sphere, its center of gravity will be the middle point. Now in this object also, the center of gravity is the midpoint. So center of gravity is the point where the resultant weight is acting. Because now here, if you take an object, you can divide into small, because the object is made of small particles. So each particle experience the gravitation attraction. The main hammer force again, then every particle, excuse me, give me a second. Okay, now for example, if you consider a particle, that particle made up of small particles, right? So this each particle will experience gravitational force vertically downward. So මේ හැම force එකම පොඩි particle හැමකටම they all experience the gravitational force vertically downward. So මේ හැම එකේම resultant එක ගත්තා නම් ඒ resultant force එක act කරන ලක්ෂය තමයි center of gravity. අපිට center of gravity පාඩම තියෙන ඒකේ අපිට සවිස්තරාත්මක බලන්න පුළුවන් කොහොමද center of gravity හොයන්නේ විවිධාකාශ වස්තු වල කොහොමද center of gravity හොයන්නේ කියලා we can discuss that in the center of gravity lesson. Okay.
So in the free body diagram, can we draw the weight in anywhere or just only from the center of gravity?
If you are doing the right physics, you have to mark the from center of gravity. Okay. And it's very important. You have to consider from the mark from the center of gravity. Okay. So write down a subheading, important facts regarding the tension force. Okay, so the first point, the magnitude of the tension force depends on the other external forces. The magnitude of the tension force depends on the other external forces. The magnitude of the tension force depends on other external forces. Now, for example, if you consider this string now in this picture, so මෙන්න මේ string එකේ ඇතිවන ආතති බලය රඳාපවතින මෙන්න මේකේ ස්කන්ධය මත depend on this mass or this weight. So if you increase this mass, the tension force is also increases. Is that clear?
Yes.
Okay, so that's the first point. Second point, the direction of the tension force acting on the string, the direction of the tension force acting on the string is away from the string from both the endpoints. But තන්තුව මත ක්‍රියා කරන ආතති බලය කෙලවරවලදී තන්තුවෙන් ඉවතට කෙලවර ලක්ෂවලදී ක්‍රියා කරනවා. පැහැදිලිද? So we'll write down the direction of the tension force is always away from the string from the endpoints. It's always away from the direction of the tension force acting on the string is always away from the string from the endpoints. Is always away from the string from the endpoints. Okay. By the way, have you studied anything like line of action of force? අපි තාම එහෙම එකක් කතා කරේ නෑ නේද? Line of action of a force කියලා අපි කතා කරේ නෑ. O level වල තිබ්බද එහෙම එකක්? Line of action.
I can't remember.
බලයක ක්‍රියා රේඛාව. දැන් මේ පාඩම කරලා තිබ්බනම් ගූර්ණේ බල ගූර්ණේ පාඩමේදී කරනවා නේද? බලයක ක්‍රියා රේඛාව ඇති ලම්බ දුර බලය වැඩි කරන බලයේ ක්‍රියා රේඛාවට ඇති ලම්බ දුරින් ගූර්ණේ විශාලත්වය හොයන්න.
Yes sir.
හරිද? Okay. So එතකොට ඒකට කියන්නේ line of action of a force කියලා. හරිද? අපි මේ දක්වා එහෙම note එකක් අපේ note එකේ දාලා නැහැ. So if you want I can give a note يعني බලය ක්‍රියා කරන දිශාව ඔස්සේ තියෙන සරල රේඛාව. ඒකට අපි කියනවා line of action of force කියලා. Right? If you want I can give a note. පොඩි දෙයක් තමයි ලියන්න තියෙන්නේ. The straight line drawn in the direction of force. That's all. Okay. It is known as the line of action of the force. Do you want to write this? එතකොට මේ note එකේ නැතුව side එකේ පොඩි note එකක් කියලා දාලා ලියන්න.
Okay. Okay sir.
Okay, so line of action of force එකකට ලියන්න. The straight line drawn in the direction of the force. The straight line drawn, the extended straight line. ඒ කියන්නේ දැන් බලය මේ පැත්තට තියෙනවා නම් ඔයාලට මේ පැත්තට දික් කරන්න පුළුවන්, මේ පැත්තට දික් කරන්න පුළුවන්. The extended straight line drawn in the direction of the force is known as line of action of the force. බලයේ ක්‍රියා රේඛාව. The extended line, the extended straight line drawn in the direction of the force is known as line of action of force. හරි නේද? ලියුවා නේද?
Okay.
So then write down the next point. The line of action of tension is the line of action of the tension force is the line of action of tension force. The line of action of tension force lies the line the line of action of tension force lies along the string. තන්තුව දිගේ ක්‍රියා කරනවා. Lies along the string. ආතති බලයේ ක්‍රියා රේඛාව තන්තුව දිගේ ක්‍රියා කරයි. So you can see the line of action of these tension forces lies along the string. Is that clear?
Yes, sir.
Okay. Okay, the next point. In a light string, LIGHT, සැහැල්ලු. In a light string, the tension force in a light string, the tension force will be same at every point of the string. The tension force will be same at every point of the string. සැහැල්ලු තන්තුවක සියලුම ලක්ෂවලදී ආතති බල සමාන වේ. In a light string, the tension force will be same at every point of the string. Now suppose if this string is light, that means it has a negligible mass, so therefore no weight. සැහැල්ලු තන්තුවක්. එතකොට සැහැල්ලු තන්තුවක් නේ. එතකොට මෙතන T1 එක අනිවාර්යෙන්ම T2 ට සමානයි. ඒතර මෙතනත් ඒක අපි ගමු සමානයි capital T කියලා. ඒතර හැම ලක්ෂයෙන්ම ආතතිය capital T තමයි. පැහැදිලිද?
Yes, sir.
සැහැල්ලු තන්තුවක සෑම ලක්ෂ ආතතිය.
Sir, but in T1 it is different, right?
Sorry?
In T1?
මේකේ දැන් මම මේකේ දැන් ඇඳලා තියෙන විදියට දැන් අපි mass එකක් consider කරලා තියෙනවානේ. හරිද? The string has a mass. So the mass is m, so mg, therefore the T1 is not equal to T2. Suppose if it's massless, the string is light, then everywhere the tension will be the same. මෙතන හැමතැනම මම මෙතන T2 ගත්තා නම් මේ හැමතැනම ටෙන්ෂන් එක T2 තමයි. උදාහරණ මෙතන ටෙන්ෂන් එක 10 නිව්ටන් නම් හැම ලක්ෂයෙම ඕනෑම ලක්ෂයේ ටෙන්ෂන් එක 10 නිව්ටන්මයි.
Okay, sir.
පැහැදිලිද?
Yeah.
Okay. If you want, I can explain with intermolecular forces as well, but it's not necessary at this point. ඒ කියවන දැන් මේක තන්තුවක් අදිනකොට මොකද්ද වෙන්නේ කියවනම් අණු අතර මොකද්ද සාපේක්ෂ relative distance එක වැඩි වෙනවා. එතකොට ඒ අතර force එක වැඩි වෙනවා. Right? So now let's say here is two molecules are there. Right? It will be in now for example, if you take a material, the molecules will be there. Now if I try to apply a force, මොකද්ද වෙන්නේ මේ දෙන්න අතර පරතරය වැඩි වෙනකොට potential energy එකත් වැඩි වෙනවා. So we call that is as elastic potential energy. We will study that later, those things. Okay. So then now for example if you consider that molecules then එතකොට මොකද්ද වෙන්නේ නම් එතකොට ඒක දැන් ඇදලා තිනකොට ඒ දැන් the molecules are now not accelerating right එතකොට ඒවා stretch වෙලා එක තැනක ඉස්සරලා තියෙන. ඒ කියන්නේ දෙපැත්තට අනිවාර්යයෙන්ම බල සමාන වෙන්න ඕනේ. එතකොට හැම ලක්ෂයෙම දෙපැත්තට බල සමාන වෙනවා. සහැල්ලු තන්තුවක්. right is that clear?
Yes.
Okay. So the point we wrote, lights in a light string, the tension everywhere will be same. Okay. And then, okay, now if you consider the weight string, again, not light. If you consider if you consider a weight string, again, මේ හැම ලක්ෂයම ස්කන්ධයක් තියෙනකොට තන්තුවේ සිරස් වෙල්ලා ඇති විට තනින් තන ලක්ෂයෙන් ලක්ෂයට ආතතිය වෙනස්. Okay, I'll explain it in a different figure. So let's assume we have a string is hanged on a attached to a support, and let's say a mass is hanged at this end. So මෙන්න මේ ලක්ෂය ගත්තා නම් මෙතන wait. Now if the mass of this object is m, so its weight acts vertically downward. Its weight acts vertically downward mg. හරිද? එතකොට මෙන්න මේක තන්තුවේ 15 කලවර කියනකො මෙන්න මේ ලක්ෂය තන්තුවේ 15 කලවර. දැන් මේ ස්කන්ධය මේ කෙලවරට එල්ලලා තිනකොට මේ ස්කන්ධයෙන් ඇති කරන ආතතිය මේ ස්කන්ධයේ බරට සමානයි. because ගුරුත්වයෙන් මේ ස්කන්ධය අදිනවා mg කියන උදාහරණයට weight එක let's say 100 newton. එතකොට 100 newton වලින් පල්ලෙහාට අදිනවා. එතකොට මේ ලක්ෂය මේ ස්කන්ධය මේ ලක්ෂය 100 newton වලින් අදිනවා. එතකොට මෙන්න මේ ලක්ෂයේදී ආතතිය මම capital T කියලා ගත්තා නම් ඒ ආතතිය mg වලට සමානයි. හරිද? Do you understand that?
Yes.
Okay. දැන් මෙන්න මේ තන්තුවේ දැන් ඉහළ කෙළවරකට මෙතනට වගේ ගියා. මෙතනට වගේ යනකොට මෙන්න මේ ලක්ෂයෙන් මේ ස්කන්ධයේ බරට අමතරව මේ තන්තුවේ බරත් මොනවාද? කැරි කරනවානේ. it's ඒකයි මේ මොකද? it carries the mass of that object as well as the mass of the down part of the string. So therefore here the tension will be little bit higher than here. Understood? උඩට යන්න tension එක වැඩි වෙනවා. ඒ කියන්නේ පල්ලෙහාට දරන්න ඕන ස්කන්ධය වැඩි වෙනවා. උඩට යන්න. Did you understand?
Yeah.
So tell me if you understand well, tell me at which point of this string the tension will be maximum if this string has a weight.
At the highest point.
Sorry?
At the highest point.
Yeah, the top point. Udama kelawara lakshya. Etana tension එක maximum. Is that clear?
Yes.
Okay, so let's write down the fact. Baratantuවක් weight string එකක් vertically එල්ලලා තිබ්බම ඒ තන්තුවේ උඩට යන්න tension එක වැඩි වෙනවා. ආතතිය වැඩි වෙනවා. So let's write down. When a weight string is hanged vertically, then the tension force acting on the string, increases from bottom to top. පහළ සිට උඩට ආතති බලය වැඩි වෙනවා from bottom to top. from bottom end to top end. පහළ කෙළවරේ සිට ඉහළ කෙළවරට ආතති බලය වැඩි වෙනවා. ඒ පැහැදිලි නේද? Did you understand?
Yes.
Okay. And the next point, ඊළඟ කාරණා තමයි බර තන්තුවක්. Now let's say මේක බර තන්තුවක්. මේ සුමට තලයක තියලා ඒකාකාර ප්‍රවේගයෙන් ගමන් කරනවා. සුමට බර තන්තුවක් සුමට තලයක තියලා ඒකාර ප්‍රවේගයෙන් ගමන් කරනකොට මේ තන්තුවේ හැම ලක්ෂයෙම ආතති සමාන වෙනවා. Wait, give me a second, I'll be back. Okay. So the next case is we have a weight string. It is on a smooth horizontal surface and it moves with a constant velocity. So when it is moves with a constant velocity, then also everywhere the tension will be same, right? So let's write down that part. When a weight string is moved on a smooth horizontal surface with a constant velocity, then the tension force everywhere on the string is same. Okay. Did you understand this?
Do I have to draw the illustration.
Yeah, it will be give you some idea. And can you explain why the tension has to be same everywhere?
Uh,
Why the tension everywhere has to be same?
because every point has gravitational acceleration downward.
It doesn't affect this horizontal motion, right? Because the gravitation acceleration is acting
Yes,
vertically downwards now.
yeah. So
So it doesn't. Yeah.
velocity is applied to full string. So
Yeah, velocity is constant in in the wall string. Then how could you explain that the tension has to be same everywhere?
there's no other force acting on this.
You can say the best thing is according to Newton's first law. So if you consider here, let's say here the tension is like at this point T1, and then this point tension is T2. You can think either T1 is greater or T2 is greater, it doesn't matter whatever it is. Then I consider only this part of the, if I'm considering only this part of the string. So you can see this is the force acting on this part of the tension force acting on this part of the string by this part of the string. So here this one I have marked here, that is the force acting on this part of the string by this part of the string. Do you understand?
Yes,
එතකොට මට මේ කොටසේ තියෙන force එක මෙන්න මෙයා විතරයි. හරිද? So T2, this T2, T1, T1. එතකොට ඒ වගේම මෙතන මෙන්න මම මේකෙන් මාක් කරලා තියෙන්නේ ඇවිල්ලා මෙන්න මේ කොටස ඇවිල්ලා මේ කොටස මත ඇති කරන ආතති බලය මේ කොටස මගින්. The tension force acting on this by this. Do you understand?
yes,
So then I want to mark only on this one. So this side is this T1, T2. So then if T1 and T2 are different, means they are, now let's say suppose you can think T2 is greater than T1, then there will be an unbalanced force, right? So then the object has to be accelerated. It has to be accelerated, which tells that velocity cannot be constant. Understood?
yes,
So if the velocity is constant, means this T1 and T2 must be equal to each other. So everywhere in the string should have the same tension. If the string is moving at constant velocity, did you understand?
yes.
Okay. So there might be a possibility that you may get a question like that in essay paper. Explain why in terms of Newton's first law, why the tension everywhere is same. So I write this question here, so you can write the answer. So write down. Explain in terms of Newton's first law. Explain in terms of Newton's first law why tension everywhere on the string should be same. Why tension everywhere on the string should be same. ඒ කියන්නේ මෙන්න මේ අවස්ථාවට අදාළ සුමට තිරස් තලයක නියත ප්‍රවේගයෙන් ගමන් කරනකොට ඇයි හැම ලක්ෂයම ආතති බලය සමාන විය යුත්තේ? Explain that in terms of Newton's first law.
I don't have to the I don't have to go the other diagram, right? The like part of the spring in the upper top.
Yeah, so how could you explain is what I've explained kind of then you can say, suppose if the tension are different in the string, right? Then you can mark this T1, T2 like this, right? You draw this string and then you mark T1 and T2, and then you have to say, suppose let's say T2 is greater than T1, right? So you consider this part, yeah, you can consider this AB. Let us consider the tension forces at A as T1 and B as, yeah, let us consider the tension force at A and B as T1 and T2 respectively. And also we consider that T2 is greater than T1, right? So then now we can consider the AB part of the string and its free body diagram. So now if these two, now see if T2 is greater than T1, then there will be a unbalanced force F equals to T2 minus T1. So therefore it has to be acceleration, which says that velocity cannot be constant. Then now we can give the counter argument. If the velocity is constant, acceleration is 0, therefore F is 0. Therefore, T2 minus T1 is equals to 0. Therefore, T2 should be equals to T1. Did you understand?
Yes.
So, මුලින් මෙහෙම A, B කියලා අක්ෂර දෙකක් ගමු. Let us consider 2 points A and B, and the tension forces at A and B are T1, T2 respectively. And then you can consider the free body diagram of AB part, so which I drawn here, right? And if T2 is, now we have considered that T2 is greater than T1, no? So then it says that there is an unbalanced force in this direction. So then it says there is a acceleration, so which tells that velocity cannot be constant. But we know velocity is constant, v is constant, right? But actually v is constant. Therefore, a equals to 0 implies force is equal to 0. So therefore, if force equals to 0, then T2 minus T1 equals to 0. Therefore, T2 must equals to T1. If that this is moving at a constant velocity. Is that clear?
Yes, sir.
Okay, so it logically gives the reason why the tension everywhere should be same. The string is moving with a constant velocity, even if it has a mass. That means if it's a weight string.
Okay, sir.
Okay. So the next case, now we consider weight string on a smooth surface, but this time accelerated, not constant velocity, right? So the next point, write down.
Is this under the important facts, sir?
Yeah, all these under the important points related to important facts related to tension force.
Okay, sir.
Okay, so write down when a weight string is accelerated on a smooth horizontal surface, then the tension everywhere on the string has different values. Tension everywhere on the string has different values. Have different values, plural form. Have different values. හරිද? දැන් මෙන්න මේ අවස්ථාවේ තිරස් සුමට තලය smooth horizontal surface. So we have then the string, weight string, and applied by force and accelerated. Acceleration is A. So if this is accelerated, so the tension everywhere of the string should the tension everywhere is different, have different values. Now, for example, you can consider 2 points, A, this point, and B, this point. Okay. So here, if you consider, you can mark the tension as T1, this T1, and this point you consider T2, T2, and let's consider the AB part of this. So AB. So the free body diagram, so in this side we have the force in this direction, and this side this direction. Here this is T1 and this is T2. So now this is entire system is accelerating, means this one also accelerating. A. So in this case T1 cannot be equals to T2. Make දෙක සමානයි නම් and there is no unbalanced force to make it accelerate. According to Newton's first law, if it's according to Newton's first law, object is at rest or moving at constant velocity only, the forces are balanced. So in other case, I mean, if it's accelerating, forces are not balanced. There should be an unbalanced force. So according to F equals ma, so T1 minus T2 equals to ma. So A is not equal to 0. Therefore, T1 cannot be equals to T2. Understood? And in fact, T1 is greater than T2. එතකොට මේ තන්තුවේ මෙන්න මේ කෙලවර ආතති උපරිමයි. In this end, tension is maximum, that T max here, that T max is equals to F, applied force. Is that clear?
Yes, sir.
And in this end, the tension is minimum, T min, so that T min equal to 0. I කිව්වනම් A කෙලවරෙන් අදින්ද දැන් මෙතන ටෙන්ෂන් එක වැඩි ඇයි කිව්වනම් මෙන්න මේ ලක්ෂ්‍ය මගින් මෙන්න මේ සම්පූර්ණ ස්කන්ධයම ඈදගෙන යන්න ඕනේ. It has to pull, right? Understood? So here the tension is maximum at this point, the maximum, because it has to carry the මුළු තන්තුවේ ස්කන්ධ බරම ඈදගෙන යන්න ඕනේ. තේරුණාද?
Yes, sir.
But if you consider this end, the far back end, මෙන්න මේ කෙලවරේදී අදින්න ස්කන්ධයක් නැහැ. ඇදගෙන යන්න ස්කන්ධයක් නැති හින්දා එතන අවම ආතතිය ශුන්‍යයි. It will be 0.
Yeah.
Is that clear?
Yes, sir. I got it.
Okay. So the next point, write down. Right. Write down the next point. When a light is inelastic, when a light like GHT, like it's a hello, and inextensible. Inextensible. ඒ කියන්නේ අවිතන්‍ය අදින්න බෑ. ඒ කියන්නේ extensible means බලයක් යෙදුවම දිග වෙනස් වෙනවා. Inextensible means the length won't change. When a light inextensible string goes over a smooth pulley, so highlight this smooth term and light also, smooth pulley. Over smooth pulley, then the tension acting on the string on both sides of the pulley are same. So as example, I can consider here, let's say there is a horizontal surface. Let's say we have a box. Okay, so and then we have a pulley attached here. And then there is a string goes over this pulley. And this side, let's say a mass is connected, mg, mass is m. So if this pulley is smooth and then string is also light, so here the tension I can mark capital T. Since the string is light, everywhere on the string has the same tension, so here also will be same tension. Now since the pulley is smooth, therefore the tension here also will be capital T, so here also will be the same tension. Understood? Suppose if the pulley is not smooth, මෙතන තියෙන tension එකට වඩා මෙතන tension එක වෙනස් වෙනවා. If the pulley is rough but it's smooth, so therefore everywhere the tension will be the same. Is that clear?
Yes.
Okay, so here under here we can write if the pulley is rough, ralu. So the pulley is rough, then we can, so this is the pulley, and let us mark the wire strings. So the string goes over this pulley. Okay. එතකොට මෙන්න මේක රළුයි නම්, now here the tension is, let's say at this point T1. Okay, but here the tension will be different, T2, because the pulley is rough now. Okay, so you can note down that as well. Okay, so these are the important facts regarding the tension force. Okay, do you have any questions regarding the today's lesson?
In the last case, when the police rush,
Yeah.
is there the same tension in the same side of the side, or
No, no.
just every point
Uh,
there's a tension, different tension?
so ඒ කියන්නේ දැන් මෙතන මෙයා රළුයිනේ.
Yeah,
මෙයා රළු නම් හරිද? මෙන්න දැන් මේක ලිස්ට් වෙනකොට මෙයා මත ලිස්ට් වෙනකොට මොකද්ද වෙන්නේ? There will be a friction force.
yeah,
Due to that friction force, now here let's say the string is light, then we can write T2 minus T1 is equals to F, that friction force. එතකොට friction force එකක් තියනවා කියන්නේ මේ දෙපැත්ත ආතතිය අසමානයි. හරිද?
okay,
friction force එක 0 නම් දෙපැත්ත ආතතිය සමාන වෙනවා. T2 සමානයි T1 වෙනවා. If the friction force is 0. Understood?
yeah. So
Yeah.
I asked if we take another point next to
Somewhere here,
T2,
you mean.
yeah, like that. So
Yeah, here then
will
the
it be
tension will be T1.
okay?
Here
So in
tension
the
T1. Here tension T2. Here T2, so on, like that.
okay, okay, I get it.
Okay then. So that's all for today's session. With this, I'll conclude.
Okay.
And in the
Sir,
next class, we can start some questions based on strings.
sir, will next class is physical, right?
I didn't hear you clearly.
The next class is physical, right?
Yeah, again on Tuesday,
Sunday.
8 to 11.
No, I mean the Sunday class. There won't be there a Sunday class.
Sunday class, yeah, because actually I didn't want to give up the Sunday class, but you told like it's better to do it through online. So then also another institute
Yeah.
contact me to do classes. It's in Dehiwala. Dehiwala team from Red. So I'm starting from this Sunday. So it will be hybrid. So starting from the beginning for like after results batch.
Okay.
Okay then. If you have any
So
concerns, please let me know without any hesitation. Okay.
okay, so the
I'll give
next
you my
class is
maximum, the top priority for you. Okay. So please, if there's anything, let me know.
so the next class will be next Tuesday, right?
Yeah, next Tuesday, 8 to 11. Sometimes I may drag up to 8, 11:30. Will it be okay for you?
Can you start early, sir, if possible?
You mean earlier?
Yeah.
Tuesday I have scheduled my. It's not started yet, but from next month's first week onwards, the Sinhala medium A-level physics classes I'll be starting in Kolanava.
Okay, sir. No problem then.
So that is for the moment scheduled 4 to 7, but later it will drag up to 7:30. So if that class started means definitely I'm not
Yeah.
able to start earlier, because
Okay.
between that I have to reach home, take my dinner and stuff.
Yeah. Okay. That's
Okay then. Okay. See you. Good night.
Sir, may I send you